This is A-level further maths, further pure 1 specimen paper, question 5. This is a vectors question. We can tell straight away that it involves the cross product and the dot product, but it's a more abstract question than some of the others. They've not given us the coordinates of any points. They've not described a geometrical problem. They're asking us to give some reasoning based on the fundamental properties of the cross product and the dot product. So they start out with what looks like the scalar triple product, but what's a bit special about this is that A, the vector A, appears in two different places. Now the details are really important here, so if you want to pick up all 4 marks, then it's a relatively quick process, but you need to be careful with exactly what your reasoning is. You need to make sure that, because each of these is essentially a proof question, the 2 marks are going to be for your method and for your conclusion. So you've got to have the correct reasoning, and then you've got to have a valid conclusion in there. It may seem a bit daft to have half your marks come from writing your therefore this is true statement, but that's how a proof works, and that's how they're going to be marked. We'll look at the mark scheme in a moment. To start with, we need to understand what it means to find the dot product of a vector with the cross product of some other vector with itself. So A dot B cross A. And to do that, we need to understand what the cross product does. So the cross product between non-zero vectors gives a vector perpendicular to both. So B cross A will be perpendicular to both A and B. Each of those vectors will be at right angles to the result of doing B cross A. We use it to find the normal to a plane. Remember, if you've got 2 vectors in a plane, you take the cross product and you generate for yourself a normal vector, a vector pointing in a direction which is perpendicular to any vector in the plane. We also use it when we're trying to find the area of a parallelogram. In that case, it's the size of the vector result that we're interested in, but the direction indicates the perpendicular to the parallelogram in question. Perpendicular to both of the sides, therefore perpendicular to the entire parallelogram. So what does it mean? If B cross A is perpendicular to both A and B, then we've got a vector perpendicular to A in particular. Why is that useful? Well, the dot product between non-zero vectors gives an answer of 0 when the vectors in question are perpendicular. So we can now say that since the vector A is perpendicular to the vector we produce when we do A cross B, or rather in this case B cross A, we know that A dot B cross A must be equal to 0. Just the scalar 0. This is the dot product that's being applied. So A is a vector, B cross A is a vector, but A dot B cross A is just a scalar. It's the scalar product or the dot product giving an answer of 0. Quick tip. The calculator's got a vector mode that you can apply. So if you wanted to test this out, you could just make yourself up a vector. Doesn't really matter what. Let's make vector A 1, 2, 3. Let's define another vector. Vector B can be 5, 7, minus 2, just so they're fairly different vectors to each other. And then we can do a vector calculation. Now, if we look here and scroll down, you can find dot product is one of the options. So perhaps we put vector A in front of the dot product, and then in brackets, we're going to do vector B cross vector A. And remember, A and B vectors here, we just made up some random vectors that were non-zero. And so the chance of getting an answer as precise as this, if it were not always the case, is pretty slim. This is good indication for me that what we're looking at is in fact the right value. And if you had no idea what the value should have been, you can do this just to check for yourself and find out. And then once you know it's 0, it might be a bit easier to do the backwards reasoning and say, okay, it's 0 because, or why must it be 0? What do you know about a dot product of 0? Well, dot product will give you a 0 only when the two vectors are perpendicular. How do we know these vectors are perpendicular? And then it might remind you that the cross product gives a result which is perpendicular to the two vectors within it. So that's the first part of the question. The next part, for another 2 quick marks, given vectors A, B, and C such that A cross B is equal to A cross C, where A is not 0 and B is not C, show that B minus C equals lambda A. What I'd be tempted to do here is start with the result I'm trying to prove and ask myself what it tells me. What does this suggest? If B minus C is equal to lambda times A, where lambda is just some scalar constant, then that means that B minus C is parallel to vector A. So we need to somehow prove that. That's not a result we can take and use. That's a result we need to demonstrate the truth of. But now we know exactly what it is that it's saying. Perhaps we can reason our way towards this statement, that B minus C is parallel to A. What does it mean for them to be parallel? Well, let's come back to our definition of the cross product and remind ourselves what it means to have A cross B. What do we know about A cross B? Well, we know that A cross B is perpendicular to both A and B. Well, in particular, in this case, well, it kind of depends if B is 0 or not. But if we already know that A is not 0, so we can certainly say for sure that it's perpendicular to A. A cross B is definitely perpendicular to A, and we're going to include our reasonings. Since A is not equal to 0, A is not the 0 vector, therefore, if you take a dot product, it's going to be perpendicular to A. Arguably, even if B is 0, then the cross product of 0 is in some sense perpendicular to everything, including to A. Now, if that's perpendicular to A, we can make a similar argument for the next bit. We've got A cross C must also be perpendicular to A for the same reason. And that means they're both perpendicular to A. And we're told that they're both equal. Well, maybe we can do something with that. Maybe we can reason out what's going on with two things which are both perpendicular to A and yet equal to each other. What does that tell you about the vectors behind the scenes? Not necessarily that they're the same, although they could be. B could be the same as C, although in this case, they said B is not equal to C. So if B is not equal to C, what does that imply about the nature of B and C? Now, if you get a little stumped here, try rewriting the equation a little bit. A cross B is equal to A cross C. And we want something involving B minus C. So with a bit of thought, perhaps we can see that rewriting this as A cross B, take away A cross C, might be helpful. And because the left and the right hand sides are both vectors, when we subtract a vector, we get another vector. We get, in this case, the 0 vector. If these were three-dimensional, for instance, it will be the vector 0, 0, 0. We don't even know what dimension these are. It just tells us they're non-zero vectors. They could be two-dimensional, seven-dimensional. It doesn't matter. But one of the key properties that you need to be aware of for the cross product is that we can distribute it over addition and subtraction. In other words, we can take the cross product of B minus C, and it will give us the same as the cross product of A with B minus the cross product of A with C. We've actually used this result when we deal with the plane equation. It's a similar sort of result, R minus A dotted with N, a normal vector. So if you're dealing with a general point which you think is on a plane and another point which you know is on the plane, then if the dot product of the vector between them with the normal vector is equal to 0, in this case just the scalar 0, then that implies that the point R is on the plane. But this can be rewritten. We can pull apart the vectors to get r dot n minus a dot n equals 0. And this is often done if we're trying to reduce our plane equation to something a bit more fundamental, especially if we want to rewrite it in Cartesian form. Because once you've got a dot n on the right hand side, if a is a known vector and n is a known vector, then a dot n is just going to give some scalar, call it k. And then if you want to, you can go from here straight to the x, y, z dotted with n potentially being a vector with values p, q, and r. And we are well on our way to constructing for ourselves the Cartesian equation for a plane. Because beyond this point, it's just a case of evaluating the dot products. So just a little reminder there that might be helpful to think about. We apply this idea of expanding or distributing a dot product, and we can do the same thing with a cross product. Because we can do that with a cross product, we can make this step here. We can put these two things together. And now look what we've got. We already said that the cross product gives vectors perpendicular to both. What does it mean if it gives an answer of 0? Well, there are only a couple of ways you can get an answer of 0. If a cross product is 0, then either one of these things must be the case. One of the vectors is the 0 vector, or the two vectors in question are parallel. A good way to remember this is to think in terms of the parallelogram idea. The way we use the cross product to calculate the area of a parallelogram. The length of the vector we end up with gives us the area of the enclosed parallelogram. So if these are our vectors, A and B minus C, then the parallelogram enclosed by the vector A and the vector B minus C has area 0. The only way that can happen is either if one of those two vectors is 0, so one of the lengths of the parallelogram is 0, or if they're not 0, they must be parallel so that the two sides that are emanating from one corner of the parallelogram are actually going in the same direction. You've got the equivalent of a parallelogram that's been squashed down to 0 thickness. We just need to use the fact that we were told in the question A is not 0, and also B minus C is not 0. They've told us that by saying B is not equal to C. So we can say A is not 0, and B minus C is not 0. Therefore, B minus C is parallel to A. And the final, therefore, B minus C must be equal to lambda times A. This follows directly from the fact that they're parallel. As we said right at the beginning, B minus C equals lambda A suggests parallel between the two. Now we're just going to have a quick look at the mark scheme so we can compare our method perhaps and see where you'll be picking up the marks for this. So at the beginning, there are two marks. One is for stating that B cross A is perpendicular to A. They would allow and or B for that one, but the most important bit to use was the fact that if you take the cross product with A, we get a vector perpendicular to A. And then, because they're perpendicular, the dot product of those two must be 0. So the actual writing down that you need to do is fairly minimal, but the reasoning needs to be sound. You need to be careful and thorough with your steps. For this second part, they've rearranged in the same way that we did. So they've move the A cross C onto the left so they can write it in terms of B minus C. And that is the thing that allows us to think in terms of parallel. And that's what they've done here. They've said because we know that A is not 0 and B minus C is not 0 effectively, then we know that those two vectors we're dealing with that have a cross product of 0 must be parallel. That's how they've made the statement they're parallel, finishing with therefore B minus C is equal to lambda A. And that's how you pick up the second mark for that question.